Hey, Math 135, what's up? In this video, we're going to be looking at the problems in 7.4, where we need to use our counting techniques to do some probability problems. In all of these problems, we're assuming that we're working with a uniform sample space so that we can employ the basic probability formula that says that the number of things in our event is equal to, the probability of our event is the number of things in our event divided by the number of things in a sample space. So again, all of these examples are examples of uniform sample spaces. If I remember to, in the context of each example, we'll talk about how it's a uniform sample space, and we're going to be using the basic probability formula here. That's the key to doing all these problems. And so we're primarily going to be focused on these counting problems. All right, in number 1, we have a customer that picks a sample of 3 oranges from a crate containing 60 oranges, 4 of which are rotten. What is the probability that the sample contains at least 1 rotten orange? So we see these words at least, and most of the time in Math 135, when we see those words at least, at most, more than, fewer than, we're going to use a partition. So let's write down the cases here. We could have one rotten orange, or 2 rotten oranges, or 3 rotten oranges. All right, and so if I want 1 rotten orange, we're just choosing 3 oranges here. We're choosing 3 oranges. I have to have 1 rotten orange and 2 good oranges. If there's 1 rotten orange and I'm picking 3 oranges total, 1's got to be rotten and 2 have to be good. And it doesn't really matter what order we pick them in. We're just picking 3 oranges. And so the fact that we have 3 different oranges, we're not picking the same orange twice. There's no repetition. We have a selection set of 60 oranges, and we're not going to pick the same orange twice. This is going to end up being a combination problem. No repetition. The order doesn't matter. This is going to be a combination problem. However, we've got our selection set split into 2 pieces. We've got 4 rotten and 56 good. So we've got a partition of our selection set. There's our partition of our selection set. We're also partitioning our event, and that can be kind of confusing. When we have a combination with a partition selection set, we do all these problems using the fundamental principle of counting, or the multiplication principle, where I've got 2 stages here. Since my selection set is split into 2 pieces, we're going to have 2 stages. I got to pick my rotten orange, and then I pick my good one. So pick a rotten orange, and then pick a good one. If I want 1 rotten orange, let's see, there are 4 ways to pick a rotten orange, but just so that I have some consistency in my formulas, I'm going to use a combination. I have 4, and I want to choose 1. For my good oranges, I've got 56 good oranges, and I need to pick 2 of them. Going to go ahead and spread this out just a little bit. Okay, so that's my first case with 1 rotten orange. If I've got 2 rotten oranges, in my first stage here, I've got to pick 2 rotten oranges. And then in the second stage, I need to pick 1 good orange. For 2 rotten oranges, I got 4 rotten oranges to choose from. and I'm going to pick 2 of them. For the one good orange, I've got 56 good oranges to choose from, and I got to pick 1 of them. Or again, you could just call that 56, but we're just finding a consistency in the setups here. And then if all of them are rotten, again, we're just trying to find at least 1 rotten orange. So it could be the case that they're all rotten. We've got 4 rotten oranges to choose from, and I got to pick 3. And then I got to pick 0 of the good oranges. Okay, so we can say in this first example that the number of things in our event is, let's see, 4 choose 1 times 56 choose 2, pick 1 rotten orange, and sometimes the word and corresponds to multiplication, and pick 2 good oranges, or pick 2 rotten oranges and 1 good one. Or we can pick 3 rotten oranges and no good ones. 56 NCR 0. And then, all right, so we have the number of things in our event space. That's the numerator here. The number of things in our sample space, that's a much easier combination problem. In this case, we're just choosing 3 oranges. There's no restrictions. I guess you could also think of this combination with a partitioned, we have a partitioned selection set. A combination with a partitioned selection set is one example of a combination with restrictions. For our sample space, it's a combination with no restrictions. We got 60 oranges in our experiment, and we're just going to pick 3 of them. Okay, so that is the direct way for dealing with this problem. With any at least or at most problem, there is also a partition strategy. There's also a partition strategy where we look at the complement. In this case, our event E complement is, let's see, the opposite of at least 1 is none. No rotten oranges. And so for the E complement, number of things in E complement, there's only one case there. 0 rotten oranges. There's only one case in the complement. And if I want to use the same strategy that I used with my, again, we still have a partitioned selection set. We got 4 rotten oranges, and I'm going to pick none of them. And then I've also got 56 good oranges, and we're going to pick 3 of them. All 3 oranges that we're going to pick are going to be good oranges. All right, so there's only one thing in the partition. If I also do the number of things in my sample space, it's still 60 and CR3. Same sample space. Both of these events are in the same sample space. Got to get this equal sign in the right spot, or else it's going to bug me. And I guess I should have mentioned this up here. This is our probability of our event in this problem. One thing that we want to do here, when we find the probability of E complement, that's what we found right here. We're still interested in the probability of E, and we want to use the complement formula. The probability of E is 1 minus the probability of E complement, which in this case is 1 minus 4 choose 0 times 56 choose 3 divided by 60 choose 3. And I think in this case the complement strategy is much faster. Complement strategy is much faster. So and it's much easier to execute on the calculator, especially when you realize that this pick no bad oranges is kind of like a non-task. There's no task there. And so you really could just do the 56 choose 3 divided by 60 choose 3. All right. I think that does it for number 1. And number 2, Jacobs and Johnson, an accounting firm, employs 14 accountants, of whom 8 are CPAs. If a delegation of 3 accountants is randomly selected, there's where we can talk about randomly selected. There's our uniform sample space. Randomly selected from the firm to attend the conference, what is the probability that 3 CPAs will be selected? So here we just have exactly 3 CPAs. So we have a delegation of 3. They're all going to be CPAs. If we want to know the probability of this event, that would be the number of ways to pick 3 CPAs divided by the number of things in our sample space. If we're just picking CPAs, there's only 8 to choose from. Again, these 3 CPAs, they're not playing individually special roles. They're all going to the same conference. So the order in which we choose them doesn't matter. So this is just a selection. So this is a combination. We've got 8 CPAs to choose from. I just cannot write this morning. Eight CPAs to choose from, and we're going to pick 3. So that's the number of things in our event here. The number of things in our sample space, we're just talking about picking accountants. There's 14 accountants that could have gone on this trip, and we would have been choosing 3 of them. All right, so that one's much more straightforward. That one's much more straightforward than the previous problem. But that's, I guess, basically because we were only doing, like, the complement. The complement of this event has 3 cases. 0 CPAs, 1 CPA, and 2 CPAs. The event itself only has 1 case. Up here, if they ask us what's the probability that the sample contains no oranges, that would have been a very straightforward problem. That's what we ended up doing with E-complement. So this is also, I guess this would also be a combination with restrictions, but we didn't have to deal with the partitioned sample space here because the non-CPAs really never came into play for our event. All right, moving on to 3. Electronic baseball games are shipped in lots of 24. Before shipping, a quality control inspector randomly selects a sample of 8 from each lot for testing. If the sample contains any defective games, the entire lot is rejected. What is the probability that a lot containing exactly 2 defective games will be shipped? So the idea here is there's 24 games, and in this particular lot, 2 of them are defective. When we pick the sample, neither of those 2 is in the sample, because if it were, the lot's rejected. It wouldn't be shipped. All right? And so they're basically asking if 2 bad, 22 good, what is the probability of 0 bad out of 8? All right, again, there's a sample of 8 that they're going to test out of the 24. And if this lot's going to get shipped, then none of the 8 are going to be bad games. All right, so we're just selecting 8 games. Selecting 8 games. For our sample space, so the number of things in our event divided by the number of things in our sample space. the sample space of this experiment is just pick 8 games out of the 24. That's a combination. So from the 24 games, select 8. The order in which they're selected doesn't matter. For our event, if there's none of them are bad, then all of them are good. All 8 are good. And so our event, we're just choosing, we're still picking 8, but we're only picking those 8 from the good. So the numerator here would be 22 choose 8. So yeah, I guess all 3 of these problems on this first page were combinations. I would describe them all as combinations with a partition selection set. The selection set in number 1 was the 60 oranges that we partitioned into 4 rotten and 56 good. In number 2, the selection set was the 14 accountants. We had 8 are CPAs and 6 are not. 6 are not CPAs. That was our partition of that selection set. In number 3, we have a selection set of 24 games, and it was partitioned into 2 bad and 22 good. And then in each one of these cases, we were choosing things from the selection set without repetition. That's why there was combinations. So all 3 of these problems are those combinations with a partition selection set. It was just that the event in number 1 was one of these at least problems where we also had to break up the event into cases, or partition our event in addition to our selection set. So I guess the point is that 2 and 3 look a lot easier, but the reason that 2 and 3 are easier than 1 is because 1, we didn't have to partition our event because this was exactly 3 CPAs in number 2, or exactly 0, again, exactly 0 bad games in number 3. And so that was one thing. There was only one case, and in number 2, I wasn't choosing anything from the non-CPAs. In number 3, I wasn't choosing either one of the bad games. I was only, like my numerator, I was actually only picking from a reduced selection set. So that's another way to describe, that's one way to distinguish 2 and 3 from 1. So the challenge with some of these counting problems is distinguishing the problems from one another, not by the stories, but from, I guess, the essence of the story. And so I guess while I would characterize 1, 2, and 3 as all being combinations from a partition selection set, in 2 and 3, because of the very special nature that the numerator selection in both of these was from a reduced selection set. So you can think of 2 and 3 because, again, in 2 I was picking all CPAs from the accountants, and in 3 I was picking all good games from the batch of 24. You could think of 2 and 3 as being combinations from a reduced selection set. And those problems are specific to, well, I guess those can be counting problems. I was about to say they're specific to probability problems, but I guess they could be just straight up counting problems too. Notice up here, our complement. You could think of our complement as being a combination from a reduced selection set. We weren't picking any of the rotten oranges in our complement up here. So our complement problem in number 1 was the same kind of problem as the problem in 2 and 3. Even though in number 1 we were talking about oranges, and in 2 we were talking about accountants, and in 3 we were talking about video games. So the stories were different, but the ideas were exactly the same in all 3 problems. All right, let's move on to the second page. In 4, a student studying for a vocabulary test. I don't know why word is, or maybe I just have too many spaces. Yeah, okay. A student studying for a vocabulary test knows the meaning of 12 words from a list of 20. If the test contains 10 words from the study list, what is the probability that at least 8 of the words on the test are words that the student knows? So again, one of the things that jumps out at me right away is at least 8. I also see that we have a selection set of words. There's 20 words in our selection set, and that's partitioned for us. The student knows, I guess we could say 12 known. 12 known, and I guess that means 8 unknown. I guess we'll call it known complement. 8 unknown. So there's a couple things going on. We have some ideas going on here. All right. So let's see. We can break this at least 8 down into cases. So at least 8 means, all right, 8 known and 2 unknown. Or I guess we could have 9 known and 1 unknown. Or we could have 10 known and 0 unknown. The student could know all 10 words on the vocab test. Now, I guess on the first problem that we did, we spent a lot of time chasing these partitions, and then we said, hey, wait a minute, that complement was really easy. And so let's think about the complement here first. Maybe we can see straight up that our complement is easier. Our event itself has 3 cases. Our complement would be fewer than 8 words. Our complement event here would be the number of knowns is less than 8. The event itself would be all of the tests where the number of knowns is greater than or equal to 8. And I think it's not too hard to see. All right, our complement event has 8 things in it actually. 0 known words, 1 known word, 2 known words, 3 known words, yada yada, up to 7 known words. That's the complement event. So there's 8 things, 8 cases in the complement event. So the complement event is going to be the more challenging one in this case. So we're going to go ahead and stick with our event. We're just going to find this thing directly. All right, so if I want to find the number of ways to get 8 known and 2 unknown, again, here's where we have our combination from a partition selection set. The order in which the words show up on the vocab test don't matter. It's just what words. The words that are on the test is the only thing that matters, not what order. And so we have to have, all right, 8 known from the 12 known words. I have to choose 8. And then I also have to pick from the 8 unknown words. I have to pick 2. By the way, this is one of these examples where the words, the symbols that I write here are not nearly as important as the words I just said and the words I'm about to repeat. From the 12 known words, we're going to pick 8 of those to be on this test because the test has 8 known words. And from the 8 unknown words, there's going to be 2. All right, for the number of ways to have 9 known words and 1 unknown word on the test, let's see there. From the 12 known words, I have to select 9. I'm picking 9 unknown words. That's the whole point. 9 known words. And then I could also do 8 choose 2. 8 choose 2, or I could just say, hey, from the 8 words, I just got to pick 1. So there's 8 ways to pick 1 unknown word. You don't have to necessarily do everything with combinations. If you're only choosing one thing, that's kindergarten counting. kind of interesting where like just choosing one thing is a thing that you can do in kindergarten, but choosing two things, that's something that we need a college degree to handle, I guess. All right. For this last case, this 0 unknowns is not really that's not really a task, so let's not even worry about it. Choosing 10 known words. From the 12 known words, we have to choose 10. By the way, this zero unknown words, it's the same thing that we did in 3 and 2. We could say choose 3 CPAs and then 0 non-CPAs, but the 0 non-CPAs is not really a task. Or down here, we could have said choose 8 good games, and then 0 bad games, but that's not really a task. All right, so we'll go ahead and if the 0 unknown words is not really a task. All right, so let's see. We just found the number of things in our event, the number of ways. I didn't put that where I wanted it to be. We're ultimately trying to find the probability of our event, and we're using our basic probability formula that we can apply for the uniform sample space. Here it doesn't say in the story, but we have to assume that the test is being made, the words on the test are chosen at random. All right, we just found the number of ways to make a test with 8 known words. That's again 12 NCR 8 times 8 NCR 2 plus, that's the or, that's the part of the partition here, plus 12 choose 9, 12 choose 9 times 8 plus 12 choose 10. And then in the number of things in our sample space, this is where this is just the number of, again, the event itself is the number of tests with at least 8 known words. The sample space itself is the number of tests. How many different tests can we make with 10 words on it? Well, there's 20 words. There's 20 words that are available, and we have to choose 10 of them. Notice here that, let's see, the number of things that are being chosen in the denominator is the number of things that is chosen in the numerator. And here, number of things chosen in the denominator is the number of things chosen in the numerator. If we go up to this version, the number of things chosen in the denominator 3, that's 1 plus 2 here. 3 is 2 plus 1. 3 is 3 plus 0. All right, so in this last problem, 10 is 8 plus 2. 10 is also 9 plus 1, but we can't see that because we didn't use the same pattern here with our combinations. All right, so yet another problem that boils down to combinations from a partition selection set. And in this case, because of the at least part of our event, we additionally had to partition our event. Number 5, an exam consists of 10 true or false questions. If a student guesses at every answer, what is the probability that he or she will answer exactly 7 questions correctly? So I guess there's 2 parts, exactly 7 or at least 7. There's 2 parts of this question. All right, so let's talk about the exactly 7 probability that the number of correct equals 7. All right, now it might seem weird, especially when we go to look at our sample space. This is one that's weird because our sample space, let's look at the sample space first. Our sample space is just the number of true or false tests with 10 questions. It's the number of true or false tests with 10 questions. And so we could think of that as a multiplication principle problem with with 10 tasks, one for each problem. Did I get 10? 1, 2, 3, 4, 5, 6, 7, 8. I got 10. And then since it's a true or false, there's 2 possibilities for each question. So that'd be 2 to the 10th. There's 2 to the 10th true or false tests with 10 questions. Now the probability that we, or I guess I guess that's not really the right way to think about that. I guess you could say that there are 2 to the 10th true or false tests with 10 questions, but for any true or false test with 10 questions, there's 2 to the 10th different ways of answering it. I guess that's the better way of thinking about it. For each of the 10 questions, you have 2 different ways of answering it. And that's why there's 2 to the 10th different ways to answer this true or false test. That's the better way to think about it here. All right. Now, some of those 2 to the 10th ways have 7 correct responses. And the strategy here for thinking about this, it's a little bit unintuitive, but this is also a combination problem. Okay, if we look at the number of ways to choose 7 correctly, since it's a true or false test, this really amounts to just pick 7 questions to answer correctly. Pick 7 questions to answer correctly. Now, I guess this is another part that's unintuitive. Obviously, the questions are numbered, I guess. But the point, like when I say that the order doesn't matter, the order in which you pick the 10 questions, like for instance, let's break this down and say we wanted to answer two of them correctly. And one of the ways to answer 2 correctly is problem 1's correct and problem 2 is correct. The order in which we answer those questions doesn't matter. If I answer 1 correct first and then 2 correct second, that's fine. If I answer 2 correctly first and then finish the rest of the test and then come back and answer number 1 correctly, I still get the same result. So the order in which we pick the questions to answer correctly doesn't matter. And you can't answer the same question twice. So no repetition. The order doesn't matter. This is a combination problem. All right. From the 10 questions, I have to choose 7 to answer correctly. And then the other 3 have to be incorrect. There's really no choice for the other 3. All right. And so the probability that the number correct is 7 will be 10 choose 7 divided by 2 to the 10th. Our sample space itself was not a combination problem, but the event was. Okay, for the second part, if I want to know, let's just talk about the event that consists of the number of correct is at least 7. We'll need to partition that into the, 4 cases. The number correct is equal to 7. The number correct is equal to 8. The number correct is equal to 9. Or the number correct is equal to 10. thinking quickly about the complement, anytime we have one of these partitioned events, we also want to think about the complement. In this case, the complement has 7 things. The number correct is 0, the number correct is 1, number correct is 2, number correct is 3, number correct is 4, number correct is 5, number correct is 6. There's seven cases for the complement. So we're not going to look at the complement here. We're just going to look directly at the event. Now we just found the number of ways to get exactly 7. That was 10, choose 7. And it shouldn't be too surprising, I'm jumping ahead here, that the number of ways to get exactly 8 correct is 10, choose 8. Get 8 correct. The number of ways to get 9 correct is 10, choose 9. And the number of ways to get 10 correct answers would be 10, choose 10. NCR 10. All right, and so if we want to know the probability of our event here for the at least 7, we can add up all these cases plus 10 NCR 8 plus 10 NCR 9 plus 10 NCR 10, and then divide by the number of things in our sample space, 2 to the 10. So yeah, this number 5, it looked like it could have been, it looked like we could have treated it like, since we had correct answers and incorrect answers, it seems like maybe we've got a selection set with a partition, but they're really, like, what are you selecting here? I guess we're selecting problems, and the problems themselves are not partitioned in any way. I guess for an individual, when we got correct problems answered correctly and incorrectly, but that's only after the selection. That's only after the selection. We still, when we're selecting, we still have all 10 problems to choose from. So our selection set is not being partitioned here, again, even though it might look like it is. In the previous problem, our partition set was partitioned before the selection. Before any problems were chosen for the test, this student knew 12 of them and didn't know 8 of them. That happened before any of the test questions were chosen. In this problem, our partition happens after the selection. After we've chosen the 7 problems to be correct, then the other 3 are incorrect, and we have our partition there. So, yeah. All right, moving on to number 6, which is the last one on this page, and the last one we'll do on this video. We're going to split this one up into 2 videos. The staff at BuzzFeed consists of 14 females, 7 of whom are white, the rest of whom belong to one or more racial or ethnic minority. And they're going to line up at random for a group photo. So there's that at random. We know we've got a uniform sample space here. The arrangements are random. What's the probability that the staff is perfectly segregated? That means all the white staff members are on one side and all the minority staff members are on the other side. So we're lining these up. We're lining these people up for a picture. So we're arranging them. This is an arrangement problem. We're talking about permutations here. All right. So when we look at our samples, the number of things in our sample space, that's just a permutation of these 14 females. You could say 14 permute 14 because all of them are going to be in the picture. Or remember, there's an easier way to get at that. It's just 14 factorial. So that's the number of things in our sample space. But our event here, our event in part A, which I guess I'll just call event A, is a permutation with restrictions. In this case, the restriction is that all the white staff members have to be on one side of the picture and all of the minority staff members have to be on the other side. So that's the restriction here. Now we've also we've also partitioned our selection set into the white staff members and the minority staff members. So this is I think we talked about this in one of the videos back when we were learning about these counting. This is a partition with this is a permutation with a partitioned selection set. And the strategy that we use here is we break this down into a multiplication principal problem. The first two tasks are to arrange. We're going to go ahead and arrange the white staff members and arrange the minority staff members individually. We're going to treat those groups individually. So let's see, there's seven white staff members, so there's 7 factorial ways to arrange the white staff members. And then there's also, since there's 14 total, 14 minus 7 is also 7. There'll be 7 factorial ways to arrange the minority staff members, because again, there's 7 in each of those groups. So once we got them arranged, then we have to arrange the groups. Either the white staff members are going to be on one side and the minorities on, the white staff members on the left and the minority staff members on the right, or the other way around. Actually, we just found that there are 2 different ways of that. Since there's 2 groups, there's only 2 ways to arrange the groups. Or you can think about it as being 2 factorial. 2 factorial is the same as 2, since we're doing a permutation of 2 things. All right, and that's how we're going to arrange the groups. I guess that's it. We arrange each group individually, and then we arrange the groups. Again, go back and look at, I can't remember what video it was. I think it was probably the 6.4 video, 6.4 supplement, when we were looking at, the Colts lining up to go to lunch. We did, and I think in the video we did a couple different examples of these permutations with a partition selection set. Anyways, when we go to find the probability, again, if we just line them up at random, what's the probability that we got all the white people on one side and all the not white people on the other side? That's going to be the number of things in our event divided by the number of things in the sample space. That'll be 7 factorial times 7 factorial times 2 factorial, all over 14 factorial. In B, what is the probability that the staff is perfectly integrated? So no pair of white staff members standing next to one another. So basically it goes white minority, white minority, white minority. They're alternating. And the idea here is basically the same. I guess there's a clever way. We could let's just do this using a fundamental counting principle. Okay? We could say, and let's break this into 2 cases. So we'll say, all right, there's a white staff member on the left, and I guess that forces a minority to be the furthest on the right, or we could have a minority starting on the left. All right, so if we start with a white person on the left, there's 7 white people to choose from. The next person has to be a minority because we got to alternate, and there's 7 minorities to choose from. Then the next person has to be a white person. There's 6 to choose from. And then the next person has to be a minority. So we're going white, minority, white, minority. The next person has to be white. There's 5 left. The next person has to be a minority. There's 5 minorities left. And then 4 white people, 4 minorities. Next person has to be white. There's 3 left. And then a minority. There's 3 minorities left. And then 2 white people, 2 minorities, and then the last 2, there's just one person, one white person left, and 1 minority left there. Okay, so there's a just using the multiplication principle way of figuring out how many different ways are there to line this staff up so that they're alternating. If we think about let's for the minority first, let's think about this another way. Let's think about arranging that group first. Arrange the minority group. There's 7 factorial ways to arrange the minority, and then another 7 factorial ways to arrange the white staff members. And then we're going to shuffle them. Once we arrange them both, then we're just going to shuffle them. So we arrange them individually first and then just shuffle them. So yeah, I guess I have no other way of describing it other than to shuffle after the arrangement. And if you look here, we got 7 times 6 times 5 times 4 times 3 times 2 times 1. There's the 7 factorial ways of arranging the white people, and 7 times 6 times 5 times 4 times 3 times 2 times 1, the 7 factorial ways of arranging the minorities. We just shuffle them differently than we did the first time. And so the really clever way of just finding the number of things in our event is to say, all right, 7 factorial, arrange the white people, times 7 factorial ways to arrange the minorities, times 2 different ways to shuffle. Shuffle with a white person first, or on the left, or shuffle with a minority on the left. And it turns out that the probability of a perfectly integrated picture ends up being the same. 7 factorial times 7 factorial times 2 factorial over 14 factorial. So it's equally likely to have a perfectly segregated staff picture as it is to have one that's perfectly integrated. All right, so that'll do it for the first half. We'll pick up the second half of this supplement in the next video.